Since the logarithm functions are inverses of the exponential functions, there are certain properties that the logarithm functions have that are their versions of the exponential properties that we are all familiar with. So we've got a list of 9 properties, or 8 properties in one formula that we're going to cover that describe how logarithms work and how expressions involving logarithms can sometimes be combined, sometimes be expanded, and can help us to solve problems and rewrite things in a more useful form for us. So throughout, let's let b be a positive number and not equal to 1. That is, let's let b be a valid base for a logarithm. Now, the first 4 properties are sort of basic properties of logarithms that we've already seen when we've talked about how logarithms are defined and what their graphs look like. So part 1, the logarithm base b of 1 is equal to 0. No matter what base we're working with, if we evaluate the logarithm at 1, we get 0. And this is because b to the 0th is always equal to 1 for any valid base b. We also have the log base b of b is equal to 1. And this is because any b raised to the first power gives us b back. Now these two we already saw last time by noting that the points 1, 0 and b, 1 are always on the graphs of the logarithm with base b. Properties 3 and 4 are based on the fact that the logarithm and the exponential function are inverses of each other. Now remember that one of the things that means is that if we compose the two functions, that is, say, apply the exponential function and then the logarithm function, as in part 3 here, the two functions undo each other. If I have the log base b of b to the x, that's always just x. And similarly, if I take base b and raise to the logarithm with base b of x, that's also always just going to be x. And again, that's because the logarithm and the exponential are inverses of one another. Now we should specify that item 3 here is for all x because the domain of the exponential function on the inside is all real numbers, whereas part 4 here is for all x greater than 0. And that's because that's the domain of the logarithm function with base b. Let's see a couple of examples of using the basic properties. If I have log base 7 of 1, that's just going to be 0, no matter what. If I have log base 3/4 of 3/4, that's going to be 1. Log base b of some number, of that same b rather, is just 1 back. Now if I take log base 2 of 16, that's the same as log base 2 of 2 to the 4th. And so by property 3, we've got the 2 to the 4th, an exponential function inside the logarithm, and with base 2 and the logarithm of base 2 on the outside. Those two exactly cancel each other out and just give 4 back. Similarly, if I have 5 raised to the log base 5 of 3, that's going to give me 3. Now in this case, I don't actually know what the log base 5 of 3 is as a decimal. It's some number. It's going to be less than 1 because 3 is less than 5. But other than that, I don't know exactly what it is. Furthermore, we're actually going to need one of the formulas we're going to see later to even approximate this in a calculator or a computer, because most calculators or computers do not have a log base 5 function. Most calculators and computers have at most 2 different logarithm functions, one for the common logarithm and one for the natural logarithm. So these are the basic properties of exponentials that we that we need to know and we can use to simplify things. Next, we're going to look at what happens when we take the logarithm of a product or a quotient. And these are going to be based on some of the properties of exponentials that we know. So, more properties of logarithms. Now, let's let m and n be positive numbers. If we take the logarithm of base b of m times n, that's the same as log base b of m plus log base b of n. So part 5 here is saying that the logarithm of a product is the sum of the logarithms. A product inside the logarithm gives us a sum outside. This is called the product rule for logarithms. First, a note, this rule only works for a product inside the logarithm becoming a sum outside the logarithm. So, for instance, this doesn't say anything about expressions of the form log base b of m plus n. This property doesn't say anything about that. And it also doesn't say anything about an expression of the form log base b of m times log base b of n. Now we also have a quotient rule. If we take logarithm with base b of a quotient, m divided by n, that's the same as log base b of m minus log base b of n. And now once again, be careful. This formula doesn't tell us anything about expressions of the form log base b of m minus n or log base b of m divided by log base b of n. Although be on the lookout for that second expression there. We're going to see something like that at the end of the video. All right, so let's see if we can prove 5. Let's see if we can see why it's the case that log base b of m times n would be log base b of m plus log base b of n. Let's let x equal log base b of m and y be log base b of n. B, m, and n are all positive numbers, and so these expressions are all nicely defined. Now, if we convert these into their exponential forms, we get that b to the x is equal to m, and b to the y is equal to n. Now, the formula in property 5 involves m times n, so let's see what happens if we multiply m and n together given these expressions. We have that m is b to the x, and n is b to the y. And now we're going to use the property of exponents, that is the exponential form of the product rule for logarithms that we have up in property 5. B to the x times b to the y is equal to b to the x plus y. This is a basic property of exponential expressions that we've seen before. So, if we just write down the first and the last steps of this equation, we have that mn is equal to b to the x plus y. But this is an exponential expression which we can convert into a logarithmic one. The logarithmic form of this expression is log base b of mn is equal to x plus y. But let's remember what x and y were. X is log base b of m, y is log base b of n, and so this means that the logarithm of base b of m times n is equal to the logarithm of base b of m plus the logarithm with base b of n. Now, My point in going through this is to show that there's not really any dark magic or anything going on behind these formulas. These really are just restatements of the relationships that we're familiar with exponential expressions, just through the lens of the logarithm. The exponentials and the logarithms are expressing the same information, just coming from different directions. So let's see how we can use the product and quotient rules in order to expand and combine expressions together. Let's expand the expression logarithm of x times y divided by z. Now, when a problem tells you to expand like this, what it wants you to do is to write down this expression in an equivalent form, but where each one of the terms involves just a single logarithm of as simple an expression inside as possible, just a single term. Just a single factor, I should say. Now, the reason we might want to do this is that sometimes we're working with mathematical principles that are easier on just single logarithm expressions, simple logarithm expressions, rather than complex ones like this. So, the way that we do this is as follows. We look at logarithm of xy over z, and here notice I'm using common logarithm because I haven't specified a base. We want to work sort of from the outside in. We look at the whole expression on the inside, xy over z, and we ask ourselves, okay, what's the biggest thing that's happening here? The big thing that's happening is that we've got the xy on the top and the z on the bottom, and that division, that quotient there, is the operation that's incorporating everything in the problem. We also have that product between x and y, but that product only involves x and y. It doesn't involve the z. You want to look for the operation that involves the whole expression on the inside of the logarithm. So, by the quotient rule, we can write this down as the logarithm of x times y minus the logarithm of z. The numerator comes out at first, and then we subtract the logarithm of the denominator. Now we can go further. Now we can look at each one of these logarithm expressions and say, can we expand them out further? And we can. This first logarithm we can expand using the product rule. And by the product rule, the logarithm of x times y is the logarithm of x plus the logarithm of y. And then, of course, we still have minus the logarithm of z on the outside. And so what we have at the end of this problem is that the logarithm of x times y divided by z is the same as the logarithm of x plus the logarithm of y minus the logarithm of z. One way that this problem is sometimes given is in the following way. Evaluate the logarithm of xy over z if the log of x is equal to 6, the log of y is equal to -3, and the log of z is equal to 2.5. So in this case, we could solve this problem by taking the logarithm of xy over z, writing it as the logarithm of x plus the logarithm of y minus the logarithm of z, and then we can look at what the problem tells us that each one of these values are. The logarithm of x is 6, the logarithm of y is -3, and the logarithm of z is 2.5. So we have 6 minus 3 minus 2.5 is 0.5. So even though we don't know what x and y and z are, if we know their logarithms and we can expand out an expression involving all of them, then we are done. Then that we're able to evaluate that logarithm. Some problems, though, ask you to combine a long expression into a single logarithm. So let's combine the expression the logarithm of a minus the logarithm of b plus the logarithm of c into a single logarithm. And while I'm using the common logarithm here, the same would work for any base logarithm that we used. Now, the thing to remember here is that we're still going to use order of operations principles when we're combining our logarithms together. And in order of operations, when we've got a bunch of addition and subtraction left, as we do here between the logarithms, we have to handle them from left to right. And this is very, very important. If we tried to group up the second and third terms together first, we would likely make an error. It's very difficult to make sure and do that properly. Moving from left to right is the best way to go. So our first step is going to be to combine these two logarithms together. Now the quotient rule is what's going to give that to us. By the quotient rule, the logarithm of a minus the logarithm of b is equal to the logarithm of a divided by b. And now we've got two terms, the logarithm of a divided by b plus the logarithm of c. And now we can use the product rule to say that if I have the logarithm of one thing plus the logarithm of another, then we get the logarithm of a over b times c. Or, simplifying it down, the logarithm of ac over b. So this is all great, but what if our expression was just a little bit different? What if instead of it being log a minus log b plus log c, it was log a minus 2 log b, or plus 1/3 log c, something like this? Well, we need something else. We need a new property. So we had our four basic properties. Then we had the product rule and the quotient rule. The next thing that we're going to look at is the power rule. So property 7, this is going to be the power rule, and it says for any positive m, we still have positive m, and any real number p at all, positive or negative, we have that the logarithm of m to the p is equal, logarithm base b of m to the p is equal to p times the logarithm base b of m. And this is called the power rule. And so let's see what this is saying. This is saying when the inside of your logarithm is some expression m raised to a power, then that power can come down in front of the logarithm, can move from inside the logarithm to multiplying in front of it. Similarly, if we go the other direction in the equality, if we have some constant that's multiplied on the outside of a logarithm, we can move it inside the logarithm as an exponent on the stuff inside. Now, a warning that the power rule only applies when the exponent is applying to everything inside the logarithm inside. So for instance, if I took log base 3 of x plus y squared, this is just fine. This is 2 times log base 3 of x plus y. On the other hand, if I had log base 4 of x times y squared, this does not equal 2 times log base 4 of xy. And the reason is that this squared here isn't applying to everything inside the logarithm. This 2 is applying only to the y, not to the x. If we had parentheses around the product xy before the squared, we could pull the 2 out in front, but the way that it's written here, we can't. So you can only use the power rule when the power inside the logarithm is being applied to everything else inside the logarithm. And let's see a proof of this. Let's let x equal log base b of m to the p. Let's let y equal log base b of m. Now, again, exchanging those for their exponential forms, that means that b to the x is equal to m to the p, and b to the y is equal to m. Those are just the exponential forms of the logarithmic expressions. Now, if b to the y equals m, that means that in this left-hand expression over here, instead of writing m, I could write b to the y. And so I get that b to the x is equal to b to the y to the p. And the exponential property we're going to use here, which is what the power rule for logarithms is reflecting, is that if I have b raised to the y and then that all is raised to the p, that's the same as b raised to the y times p. But we know that the exponential functions are 1 to 1. So if we have that b to the x equals b to the yp, that is, if the two outputs to the exponential function, b to the x and b to the yp, are equal, that means that the two inputs of the exponential function are equal, or in other words, if two exponential functions are equal and they have the same base, then their exponents have to be equal also. So this means that x is equal to y times p, or I'm actually going to write it as p times y to make the next step even clearer. So given all this, x has to equal p times y, but x was exactly the logarithm with base b of m to the p, and y was exactly the logarithm with base b of m. So that exactly gives us the power rule. The log of m to the p is equal to p times the log of m. Let's see how we can apply this. So if the logarithm base, or let's do this, if the natural logarithm of 2 is approximately 0.69, and it turns out it is, then what is the natural logarithm of 32? Well, we can do this using the power rule, because the natural logarithm of 32 is equal to the natural logarithm of 2 to the 5th. 32 is 2 to the 5th. Now, this power 5 here, we can bring down in front. This is equal to 5 times the natural logarithm of 2. Now, the natural logarithm of 2 we have up above is approximately 0.69. So we have 5 times 0.69 will be 3.45. And so we have that the natural logarithm of 32 is approximately equal to 3.45. So this is the sorts of things that we can do with the power rule. However, possibly more importantly, we can use the power rule to expand and condense logarithmic expressions like we had before that are more complicated. Let's take an example. Let's try to expand the log base 3 of x plus 2 cubed times x minus 1 to the 7th over x to the 15th. We're going to follow the same sort of standard that we did before, where we're going to move from the outside in. We're going to say, all right, what's the biggest operation that's happening inside the logarithm? In this case, the biggest operation happening inside the logarithm is, again, that big division. It's the big fraction bar we see there. So by the quotient rule, we can say that this is equal to log base 3 of x plus 2 cubed times x minus 1 to the 7th minus log base 3 of x to the 15th. Now, when we look at this first logarithmic expression here, notice that we can't use the power rule. There are two exponents that we see inside the logarithm expression, but neither one of them applies to everything inside the logarithm. The exponent of 3 only applies to the factor x plus 2. The exponent of 7 only applies to the factor x minus 1. And so neither one of them apply to the whole thing. However, we can use the product rule on this. So we'll go ahead and use the product rule on this first term. I'm going to leave the second term alone for this step. So we use the product rule to get the log base 3 of x plus 2 cubed plus the log base 3 of x minus 1 to the 7th. That's what that first logarithm term turns out to be. And this is minus log base 3 of x to the 15th. Well, now we've got a bunch of terms which we can apply the power rule to, because inside each one of these logarithms is some expression raised to a power, and that's it. And that's the only thing inside the logarithm. So by the power rule now, we can take this 3 and bring it down in front of the logarithm. We can take this 7 and bring it down in front of the logarithm. Take this 15, bring it down in front of the logarithm to get 3 times log base 3 of x plus 2 plus 7 times log base 3 of x minus 1 minus 15 times log base 3 of x. And now, where can we go from here? Nowhere. We have no rules that tell us what to do with logarithms of sums. We know how to handle a product inside a logarithm, a quotient inside a logarithm, or a power inside a logarithm, but not a sum and not a difference. There are no general formulas that tell us a way to simplify log base 3 of x plus 2. So we have to leave it that way, but this is a useful thing that we've done. One might ask, well, which form should we put an expression in? If we have an expression like the one that we started with, should we change it into a string of logarithms like we just did? Or should we leave it as a single logarithm of a complex expression inside? And the answer is, it depends. It depends on what you're doing with this expression, or in this case with variables, with this function. In some cases, for instance, if you're solving equations involving logarithms, an expression like the one that we started with is usually easier. If you're solving equations involving logarithms, typically you like seeing a single logarithm with all the stuff inside it. That turns out to be easier. On the other hand, there are some situations where what you want is to have a whole bunch of terms that are each as simple as possible. This is, for instance, the situation we run into when we get to calculus. In calculus, many of the things that we do are easy to apply to sums of simple expressions. So, for instance, handling the last expression we have here, it's just 3 terms, and each term is really simple. That's easy. But a single complicated expression, like we have at the beginning of this problem, is harder and is not what we want to do at all. So the answer is it depends. Which one of these is preferable? Depends on what you're doing with it. So let's see an example going the other way, because sometimes you will have a big, long expression and you want to combine it down into a single logarithm. So let's combine the following expression into a single logarithm. And let's do 2 times log base 5 of a minus 1/3 times log base 5 of b plus 17 log base 5 of c plus d. Now, we're going to do this sort of in the opposite steps that we did the first one. So our first step here is going to actually be to use the power rule to take each one of these coefficients in front of the logarithms and bring them up as the exponent of the terms inside, because we're not going to be able to combine things using the product or quotient rules until we do that. So applying the power rule, we get log base 5 of a squared, then log base 5 of b to the 1/3, and then log base 5 of c plus d to the 17th. When the expression inside your logarithm is more complicated than a single variable, make sure to put parentheses around it so that you indicate correctly that the number that you've moved from in front of the logarithm inside is in fact a power of the whole expression together. Now at this step, of course, we want to do it the same way we did before, moving left to right using the product or quotient rules as appropriate. In this case, we have a difference of logarithms, which means that we're using the quotient rule. A difference of logarithms corresponds to a quotient inside the logarithm. And now, a sum of logarithms means a product inside. And so our final form of the answer might look something like the following. We get a squared times c plus d to the 17th in the numerator. In the denominator, we have b to the 1/3, but we'll often write that as just the cube root of b. So the big expression 2 times the log base 5 of a minus 1/3 log base 5 of b plus 17 times the log base 5 of c plus d is completely equal to the expression log base 5 of a squared times c plus d to the 17th all over the cube root of b. And transforming back and forth between expressions like this is an important skill that you should have when working with logarithms. All right, now the 8th property that we want to include in our list is one that is immediate from the fact that the logarithms are themselves an inverse function of the exponentials. Remember that a function only has an inverse if it is 1-to-1. We looked at the graphs of the exponentials and determined that the exponential functions are 1-to-1. Therefore, they have inverses, which are indeed the logarithms. But because the logarithms are inverses to begin with, they themselves have inverses. The inverse functions of the logarithms are the exponentials. And because the logarithmic functions have inverses, they are 1-to-1. We also saw that from their graph. So property 8 is that the logarithm functions log base b is 1-to-1. That is, if the log base b of x equals the log base b of y, then x equals y. All right, now the last thing that we want to look at here is how we handle expressions like log base 5 of 3, as I mentioned earlier. And most calculators that we run into only have 2 logarithm functions on it. So for instance, if you look at this calculator that I've used a couple of times, if I go over to where my logarithms are, you can see that I have an LOG button, which is just the common logarithm, logarithm base 10, and I have the LN button, which is the natural logarithm, logarithm base E, but I don't have a logarithm base 5 function. I have functions that let me take any base to any power that I want, so I can do 5 to the x, 17 to the 2, anything like that, but I don't have the same thing for logarithms. So what we need to do is to figure out how can we rewrite the logarithm function, log base 5 of 3, in such a way that we actually can use a calculator or computer to do it. And the key for that is going to be the change of base formula. There are many things in mathematics that aren't very well named, but the change of base formula is a good name. The change of base formula exactly tells you what it does. It takes a logarithmic expression and expresses it using a new expression which involves logarithms with a different base, a base that you've changed. So the change of base formula says that if a and b are positive numbers that are both not equal to 1, that is, they're both valid bases for the logarithm, and x is a positive number, then the logarithm base b of x is equal to the logarithm base a of x over the logarithm base a of b. So this gives an equation between two expressions. The expression on the left involves a logarithm of one base, b, and the expression on the right involves logarithms of another base, a. The thing that is so helpful about this formula is that we get to choose the base a. If we have some expression, log base b of x, on the left that we don't know how to evaluate, we can choose any base a that we like to rewrite it as using the change of base formula. Now, we are almost always going to use the bases of 10 or e because usually when we use the change of base formula, we're doing it so that we can plug a logarithmic expression into a calculator and approximate things that way. So let's see an example or two about how we use this, and then we'll see how we might go about proving this. So let's look at, for instance, log base 5 of 3. If I want to evaluate log base 5 of 3, what I can do using the change of base formula is I can write this as log of any base I want of 3 and log any base I want of 5. Now, you might be wondering how you can keep track of which part of the logarithm goes on top, which part goes on the bottom. The easiest way that I have seen to do this is just to note that when we write down the expression log base 5 of 3, that the 3 expression on the left literally sits higher on the page than the 5 does. And so the 5 sits lower on the page, and so it goes into the denominator of the new expression. The 3 sits higher on the page, and so it goes into the numerator of the new expression. And that's pretty much it. That's the best mnemonic I'm aware of for remembering this. And so now, I can choose any base I want here. I'm going to go ahead and choose log base 10 because that's something that I have on my calculator. So now I can actually pull out the calculator and see what this is, rounded to however many decimal places I want. And I can say, all right, I want log base 10 of 3 divided by log base 10 of 5. And if I do that, I see that this is equal to 0.6826 if I want this to 4 decimal places. And that allows me to evaluate log base 5 of 3 over, or log base 5 of 3 by expressing it using the change of base formula using log 10. But this wasn't my only option. I chose to use logarithm base 10. I could have used any base at all. Now, the only other base that's particularly relevant to this question right now is what about log base e? What if I use log base e instead? Does the answer that I get out of an expression like this depend on whether I'm using the common logarithm or the natural logarithm? Let's check. We have the natural logarithm of 3. If we apply the change of base formula with our new base being e, we wind up with the natural logarithm of 3 divided by the natural logarithm of 5, which gives us again 0.6826 to 4 decimal places. And so the answer is it doesn't depend. The change of base formula applies no matter what value of a you choose for the base. This quotient will always give you the same number, which is perhaps a little surprising to begin with, but once we see the formula, or once we see the proof of the formula, we'll note that log base b of x is always just a single number. It's perfectly well defined. It's the exponent you have to raise b to in order to get x, and so if we want to express that any other way, if we want to say that that's equal to some other expression, well, then that expression has to be equal to the number log base b of x. Log base 5 of 3 is some number, even before we decide how to evaluate it. And so this formula tells us that, yeah, these expressions are actually all going to be equal no matter what value of a you choose. They're all going to be equal to the log base b of x on the left. All right, so now let's see if we can convince ourselves that log base b of x is going to be log base a of x over log base a of b, no matter what a, b, and x are. So let's let y equal logarithm base b of x. Now the equivalent exponential form of this is that b to the y is equal to x. Now we're going to take the logarithm of base a, logarithm with base a of both sides. Because the two sides of the equation are equal, that means that if we take the logarithm with base a of both sides, those expressions are going to be equal as well. Well, now we can use the power rule. Y is sitting as the exponent of the inside of the logarithm expression on the left, and therefore we can bring it down in front. So we get that y times the logarithm base a of b is equal to the logarithm base a of x, and therefore if we divide both sides by log base a of b, what we get is that y equals the log base a of x divided by the log base a of b. But remember what y was in the first place. We introduced the symbol y to stand for log base b of x. And therefore, we have that the logarithm with base b of x is equal to the logarithm base a of x divided by the logarithm base a of b, which proves the change of base formula, which we wanted to, shows that we can compute or approximate any logarithm we like using the change of base formula by changing it into a logarithm that we can evaluate in a calculator. And those are all of the properties of logarithms that wind up being important in many of the applications that we use logarithms for.